Hey guys, Miss Marusik here, and in this video we're going to talk about calculations involving buffers. Now, a buffer solution is simply just an equilibrium system between a weak acid or base and its conjugate pair. So you could really solve these problems utilizing the same method we've used for all of our equilibrium problems, which is a rice table. You would just have a starting concentration of both your weak acid or base reactant as well as your conjugate partner that's on the product side. Then you could utilize X to show the changes that are occurring. If you had a weak acid, you could then use a Ka expression to solve the hydrogen ion concentration. If you had a weak base, you would use the Kb expression to solve hydroxide. And then once you have those ion concentrations, you can then solve pH. And that would work beautifully. However, scientists at some point figured out that you're doing the same math over and over again in those problems, as long as you have those conjugate partners present, as long as you had a buffer system. And so what they did is they said, hey, let's try and rearrange our equations to make this process a little bit faster, where maybe I don't really have to set up a rice table to calculate these buffer systems. So that's where the Henderson-Hasselbalch equation comes into play. By the way, if you're curious on how this equation got derived, here's how it looks. They took that Ka expression and basically rearranged a whole bunch of stuff around in order to get this lovely equation right here. pH equals pKa plus the logarithm of A negative, so that would be that conjugate base, over Ha, so that would be our weak acid. Now again, this equation only works if I have a buffer system. I have to have both present, the weak acid as well as its conjugate base, or a weak base with its conjugate acid. If I don't have one or the other, then I can't utilize this equation. So I have to be really, really careful. Now, from here on out, I tend to call the Henderson-Hasselbalch equation the HH equation. So if you ever hear me say HH equation, this is the equation that I'm referring to. Now, this is the format that is shown on your formula chart itself. However, a more universal way of thinking about it is, instead of saying, hey, the conjugate base over the acid, is to just think about base over acid. And the reason why I like to think about it in this manner is because technically I can use this equation for weak base buffer systems as well. Now, I will warn you, on occasion, if you have a base given, they're going to give you a Kb value, and so you may need to do some fancy math in order to figure out your Ka value for that weak base. So we'll do some problems like that here in a minute. Now, if you're given only molarity information about your substances, we assume that those molarities were recorded when the solutions were already added together. So you can plug your data straight into the HH equation at that point. However, if they did give you volume information along with the molarities, then that means the molarities were only true at those individual volumes. And so therefore, you're going to have to figure out what the new molarities would be once I add the volumes together before I can plug into the HH equation. Now, if that sounds familiar, that's the same process we did on a titration calculation. Remember the step that we needed to do in order to figure out the molarities at the new total volume? That's right, we did a voom voom, right? So you would have to do a voom voom here if you were given volume information. If you weren't, man, then you can just plug in your molarities as is and save yourself a lot of time and effort. All right, with that said, let's go ahead and flip the page and start looking at some of these examples. All right. It wants us here to calculate the pH of a buffer solution containing 1.00 molar H3CCOOH, and they give us a Ka value, with 1.25 molar H3CCOONA. And I'm like, man, these are some weird looking formulas. Like, this one looks like I'm saying Hakuna, like Hakuna Matata or something. I don't know. It's a very strange format to these, right? Well, it's because they've written these in more of an organic style format. So this right here is just simply acetic acid, HC2H3O2. They've just written it in such a way that an organic chemist could tell that this would be your Lewis structure for that substance. However, think about what we know about acetic acid. We know that that is not on the strong list of acids, so that is definitely a weak acid. And then what's happened is that this H has been lost here, and so it's been replaced by a sodium ion. So this is just simply showing sodium acetate over here, which means this H3CCOO would all have a -1 charge, and then the sodium would have a +1 charge. And so that means we have here our conjugate base present. I know at first glance it doesn't look like it, but that is actually what we have. And so I see, well, if I have a weak acid and a conjugate base, then that means I have a buffer solution present. And so therefore, if I'm trying to calculate pH, I am allowed to use the HH equation. Now, remember, the HH equation has that pH equals the pKa plus the log of the base over acid. We don't have pKa, but we do have Ka. So don't forget, if I want to take the Ka and turn it into a pKa, I would just simply take the negative log of this number. So to kind of see everything set up here, first I went ahead and wrote the equations that I would have plugged into. So again, I'm going to use pH equals pKa plus the log of base over acid. Since I don't have pKa yet, I'm going to use the negative log of Ka in order to get pKa. And so I'm just going to substitute that value in. So I came down here and I started plugging in pH equals, and instead of pKa, I put the negative log of my Ka. So that's that 1.8 times 10 to the -5th. And then I add it to the log of base over acid. Now don't forget, the base was the acetate ion here. And so it had a concentration of 1.25 molar. So that's what I put in the numerator. The acid down here was the acetic acid, the weak acid, and so that had a concentration of 1 molar. So that's how I decided what to plug in. From that point on, I just plug it in my calculator and see what it gives me. Here it gave me a value of 4.84, which makes sense because this is a weak acid buffer system, so I would expect to see a pH of lower than 7. Now it does ask us two other things here. It next wants us to write the reaction that occurs when 0.01 moles of solid potassium hydroxide is added to the solution. So again, that's adding a base to the solution. And then it also asks, would the pH be expected to be slightly increased or decreased due to the addition of the KOH? Well, let's think about this for a minute. Writing the reaction is exactly what we did on our previous video. If I have potassium hydroxide, think about which piece of this is going to interact with my equilibrium system. That hydroxide, right? That potassium's just a spectator ion. Well, would hydroxide react with the acid or the base? Well, hydroxide being a base, I would want to react it with the acid, right? And so that would get me an equation of the OH plus the acetic acid, making the acetate polyatomic ion and water. So again, this is exactly what we did on our previous video. Now, it asks about pH slightly increasing or decreasing. Obviously, this is a buffer system, so it shouldn't change all that much. It still should be pretty darn close to that 4.84 when this is all said and done. However, it is going to slightly change, and since I'm adding a base, I would expect the system to get more basic, and so therefore I would expect the pH to increase. All right, let's look at our next one here. I want to determine the pH of a buffer solution containing 0.050 molar C3NH2, which they tell me is methylamine, and they give me a Kb value. Now, if they're giving you a Kb, then that means this sucker here is a weak base. And they are giving that to us with 0.080 molar CH3NH3Cl. And I'm like, well, that's got some sort of ion in it with chloride ion. And if I look, I notice it's in common here with my other substance. So what's happened here is that this ion, which would be positive because the chloride is negative, this ion would be my conjugate acid. And so therefore, if I have a weak base plus a conjugate acid, I know I have a buffer solution. And so if I want to solve pH, then that means I can, again, use my HH equation. Now, there's one awkward thing to this problem. Our HH equation has Ka in it, but this has Kb. And so what that means is that I need to convert between the Ka and the Kb. Well, remember how we do that. We have an equation that we can use, right? Kw equals Ka times Kb. So here's my formulas I would use. First off, we know we need the HH equation, okay? But I don't have Ka. So in order to get Ka, I would utilize Ka times Kb equals Kw. So I went ahead and rearranged to solve for Ka, which would be Kw over Kb. Now, technically, this is pKa over here. And so I need to take the negative log of the Ka. So that means I need to negative log this division here, this Kw divided by Kb. All right, so let's see it with some numbers. Here's what I would have plugged in. I would have had, hey, I want the pKa, so the negative log of Kw, assuming I'm at 25 degrees Celsius, it didn't tell me otherwise. So 1 times 10 to the negative 14th, divided by my Kb, 4.38 times 10 to the negative 4th, added to the log of my base. Now here, the weak base is the base. So I use the 0.050 on top. And then I divided that by the acid. The conjugate acid had a molarity of 0.080. And again, no volumes were mentioned here, so I didn't have to do a voom dilution kind of thing. And so then I just simply plug all that into my calculator. And that gets a value of 10.44. Let's ask ourselves if that makes sense. Well, this is a weak base buffer system, and so therefore a pH above 7 does in fact make sense. All right, they ask us to, again, write a reaction that occurs here when HBr is added to the buffer solution. And would that pH be expected to be slightly higher or lower than this once I add in that HBr? So let's think about this for a minute. If I add in HBr, that is a strong acid. And I know a strong acid really is going to add hydrogen ions to this solution. So would the hydrogen ions, which are acidic, would they want to react with the conjugate acid or the weak base? Well, again, an acid wants to react with a base. So here's what would take place. Our hydrogen would interact with our weak base, and when it does so, what would happen is that it would combine with it in order to give CH3NH3+. Now, if I'm adding that acid in, the pH should remain close to 10.44. Again, this is a buffer solution, but it is going to get slightly more acidic, so the pH would decrease a little bit. Not as much as you would have necessarily expected it to, but it does still decrease some. Now, in college, you might be actually asked to calculate what that new pH is. But the good news for us is at our level of AP chemistry, we are not going to be asked to do that. Whew, I know we're relieved, right? All right, let's look at the next one. The next one says that it wants us to calculate the pH of 100 milliliters of 0.75 molar lactic acid with 50 milliliters of 0.25 molar sodium lactate. So of course, lactic acid here, being not on the strong list, is one of our weak acids. And we see that C3H5O3 in it along with the H+, and we see that piece in common over here. So this sodium lactate is containing our conjugate base. Now, here's the awkward part on this one. We do have volumes mentioned, which means that these molarities are only true at those volumes. So before I can use the HH equation, we first need to do a voom-voom calculation. And unfortunately, we've got to do a voom-voom calculation for both of these. So first, for the lactic acid, I did the 100 milliliters of 0.75 molar. My new additive volume is 150 milliliters, so I want to figure out the molarity at that 150 milliliters. And so that's what I got here at 0.50 molarity. I then did the same thing for the conjugate base. I originally had 50 milliliters of 0.25 molar, but again, now I want to figure out the molarity at the total volume of 150 milliliters. That gets a molarity of 0.083. So now, just like I did with the other problems, we're going to plug into the HH equation. But now I'm going to use these molarities instead of the original ones that they gave me. So to see that in action here, again, I'm using pH equals pKa plus the log of base over acid. So that same HH equation. Again, I have Ka. I don't have pKa yet, so I need to do the negative log of Ka. And so I just use that as a substitution in. So I did the negative log of my 1.4 times 10 to the negative fourth, added to the log of 0.083. So that is the base molarity that we calculated, over our acid concentration that we calculated of 0.5. Plug all that into my calculator. I see that gets a pH of 3.07. Ask ourselves, does that make sense? Well, this is lactic acid buffer system. It's a weak acid buffer. And so a pH below 7 definitely makes sense for that. All right, let's go ahead and flip the page. All right. It says that we have a buffer solution was prepared in laboratory. It contains 0.5 molar hydrofluoric acid, which is HF. And since they give us a Ka value, we know that this is a weak acid. And 0.50 molar sodium fluoride. Now, sodium fluoride, NaF, when it dissociates, one of the things that it would create is that fluoride ion. And so that's our piece in common between these. And so that fluoride ion would be our conjugate base. So that just confirms the fact that it is in fact a buffer solution. They want us to calculate the pH of this buffer solution, which means we're going to use the HH equation. Now, I do notice that they did not give me any volumes here, so that means I don't need to do any kind of voom-voom before I use these numbers. I assume that these are the molarities at the additive volume. So we're going to plug into HH here. Again, I have a Ka value, so I need to take the negative log of it to get the pKa. So I'm going to substitute that in for my pKa. Negative log 7.2 times 10 to the negative fourth. But then something really interesting here happens on the math. I have both 0.50 molarity of my conjugate base, the sodium fluoride, but I also have 0.50 molarity of the hydrofluoric acid, my acid that would go in the denominator. Now, when I have 0.5 over 0.5, that would equal 1. Well, the log of 1 is simply 0. So that means this entire term cancels out here. So look what happens. Our pH ends up equaling the negative log of the Ka, meaning pH equals pKa. Now, the actual number that is the answer for this problem is 3.14, but remember that pH equals the pKa. And the only other time we've seen that happen is when we talked about titration curves and the half equivalence point. So what that means is that if I had been conducting some sort of titration with hydrofluoric acid and some base that makes hydroxide, that when I reach the half equivalence point between hydrofluoric and the fluoride ion, I would have had that pH of 3.14 if the molarities were both at 0.50. Isn't that kind of interesting how that worked out, right? So we are going to talk about how all of these values correspond to titration curves. I know we haven't really talked about the correlation yet between buffer systems and titration curves, but there is one, and we're going to see that here in just a little bit. Let's go ahead and look at the next example, which is actually a multiple choice question. It says that the table below that we see right here shows the values of Ka for 4 weak acids. Which of the following pairs of chemical species, when combined in equimolar amounts, results in a buffer with the pH closest to 7.5? Well, first thing, I'm going to go and make sure that these are all buffer solutions, because if any of them aren't a buffer solution, then I can rule them out. And I notice one that sticks out to me off the bat, something that I noticed the two species don't have anything in common, and that would be this first one here. HNO2 is a weak acid, but hydroxide ion is definitely not its conjugate partner. And so therefore, I would rule that answer out. Now, all the rest of these, we do have weak acids with their conjugate present. So now, I need to think about this equimolar amounts statement. What that statement indicates is that each of these would have equal number of moles. Now, we just talked about if both the acid and its conjugate base have equal moles, then this term right here ends up being 0 and cancels out. So what that means is that if I'm looking for a pH closest to 7.5, I'm looking for a pKa close to 7.5. Now, this being a multiple choice question would have been done without a calculator. This was actually on an AP test. And you're looking at these numbers and you're thinking, well, wait, I have to take the negative log of those to figure out what the pH is, so how in the world would I do that? Well, I'm going to give you a hint. Remember, we can approximate a p-value for these by looking at our exponents. Now, none of these have just 1 at the front. If this had been 1 times 10 to the negative 4th, then your pKa or your pH would have just been 4. But we have a number other than 1 at the front. But remember, your value for the p, if this first number isn't 1, is always going to be a little bit less than the absolute value of that number. So for example, this one would have had a pKa or a pH of 3 point something something. I don't know what that something something is, and I'll be honest, it's not going to matter. You'll see why here in a minute. So for this one, you would have had 4 point something something. This one would be 7 point something something. This one would be 9 point something something. Now, look at this for a second. We want a pH closest to 7.5. Well, which of these is probably going to come out closest to 7.5? I don't know about you, but this one's looking real good right here, yeah? So, by process of elimination here, C must be the correct answer. All right, let's look at another one. This one says that a buffer solution is prepared by dissolving some solid sodium benzoate in a solution of benzoic acid. And they give us a Ka value for that benzoic acid. They also give us the pH of the buffer solution. And so they ask us what would be present in a greater concentration in the buffer solution. C7H5O2 negative, which again is coming from the sodium benzoate, or the HC7H5O2, which is my benzoic acid. Now, if this is my weak acid, then this here must be my conjugate base. However, here's kind of the awkward thing on this one. They actually already give us the pH. So what we're really trying to do here is to compare that ratio that we see at the end of the HH formula. So with that said, let's look at my work here. So first off, I wrote my equations over here. I know I'm going to need to think through this pH equals pKa plus the log of base over acid. I also know that I don't have pKa, I have Ka, and so I need to do the negative log of Ka. So what I did here is I set up what I know in my equation. I know the pH, I know that I have to take the negative log of the Ka, and then I have to do the log of base over acid. And this ratio is really what I'm trying to think about here. So then I start simplifying things, start reducing down and solving my math. So I did the negative log of my Ka to get that pKa value of 4.19. I then brought that term over. Now, since this is added here, I'm going to subtract that over. And so that got negative 0.34 when I subtracted it over. So now I need to get rid of this logarithm. And this is where I do 10 to my exponent. If I, put these both as 10 raised to that value, I can undo the log over here. And so that's what I did on this next step here. I said, hey, 10 to the negative 0.34 is going to equal 10 to the log of base over acid, and 10 raised to the log cancels out. So that just leaves me with B over A. So now I went ahead and solved this number here. I plugged it in my calculator. That got me a value of 0.46 equals base over acid. Now again, the base was my conjugate base, that C7H5O2 ion. The acid was my CH7H5O2, my benzoic acid. So if this is less than 1, what that means is that the denominator must be bigger than the numerator. The acid of the benzoic acid must be in a greater concentration than the conjugate base. So here's the deal. We've seen a few things on this page. First off, I'm going to actually fill out this middle one first. If our acid is equal in concentration to the conjugate base, or for a base, if the weak base is equal to the conjugate acid, if the original substance and the conjugate are equal, then the pH equals the pKa. You would be at the half equivalence point on a titration. Now in this example that we just saw here, the pH was less than the pKa, right? And notice what happened here with my solutions. The acid, the HA, was greater in concentration than the A-, than the conjugate base. So when this happens, as we saw up here, what that means is that my pH should be smaller than my pKa. On the flip side, I know we haven't seen one like this, but process of elimination here. If the conjugate base is greater than the acid, then the pH must be greater than the pKa. Now, hint, this all ties to titration curves. I know it doesn't seem like it, but there were places on the titration curves where the weak acid was greater than the conjugate base, where they were equal, or where the conjugate base was greater than the weak acid. We had places on the titration curve that corresponded to those exact same equalities. So with that said, let's talk about titration curves for just a moment. So if you have a weak plus a strong titration, either a weak acid with a strong base or a weak base with a strong acid, then somewhere in your titration curve, you have a buffer present. And back when we did these videos, I had you mark something called the buffer zone. And I know some of you just wrote it blindly. You're like, oh, Marusik marked this as being the buffer zone. I'm going to do that too. And I didn't really talk about it. Well, the reason why I didn't talk about it is because it really wouldn't have made a lot of sense until now. What happens is that in that zone, you technically have a buffer solution. Now, here's the cool part. If you wanted to save yourself some time on those titration calculations, and you knew for a fact that you were in the buffer zone, then you could use the HH equation in those titration problems. And I'll show you how to do that here in just a moment. However, I say this with some hesitation. I find that students try to use the HH equation all along the titration curve instead of just where it's appropriate. And so that's why I did not show this to you in the beginning. I wanted you to see the difference in each of those segments on the titration curve and how you would calculate them, because that method I showed you always works. If you try to use this equation on sections where you're not allowed to, your math is going to be all messed up and you're going to be sad because you're going to get the wrong answer. So you have to be careful. First off, this only can be used on weak plus strong titrations. It cannot be used on strong acid, strong base because those never have a buffer present. You never have a weak substance with its conjugate pair. You can't use it. Now, this can only be used in portions of the titration where the weak substance, either the acid or base, is present with its conjugate partner. So anything prior to the equivalence point. And the reason why I say that is because at the equivalence point is where you no longer have your original weak acid or base present. All of that has gone away because you've canceled it out with whatever strong substance you're adding to it. So at the equivalence point or beyond, you no longer have a buffer system. And so you cannot use the HH equation. So you have to be really careful. You have to ask yourself, well, am I before the equivalence point? And I will show you what trick you can use to kind of figure that out. Now, it says here, if you have a weak base plus strong acid titration, you will be given a Kb value for the weak base. And as we know, the HH equation does not use Kb, it uses Ka. So you do have to convert if you're doing a problem with a weak base. So you just have to be really careful if you are choosing to use the HH equation. My advice is to only use this equation if you are confident that you have a buffer solution on your hands. If you are not confident that you have a buffer solution, then don't do it this way. So with that said, let's talk about a titration curve for a moment, okay? The region that is considered the buffer zone is this area right here, anything before the equivalence point. Because when I start out, I have all weak acid over here, or weak base if I'm doing the opposite titration. And until I get to that half equivalence point, as we just said on the previous page, the weak acid outweighs the conjugate base. I haven't added enough base to get it to where those are equal yet. So before this point, the pH is less than the pKa. Once I get to that half equivalence point, where the weak acid and its conjugate base are equal, now the pH equals the pKa. Beyond that point, up until the equivalence point, now you have more conjugate base than you had of the original acid. And so here the pH is a little bit higher than the pKa. So in this zone, you could add some additional acid or base and not see that much fluctuation. That's what it means to be a buffer, right? Well, look how this curve is kind of flat in that area. So again, I'm adding acid or base, and I'm not doing much fluctuation in pH. That's the whole definition of being a buffer. Now, once I reach the equivalence point, remember, all of the weak acid has been canceled out stoichiometrically by the base that I'm adding to it. And so, since there's no weak acid left, I no longer have a buffer solution. So from that equivalence point on, I cannot use the HH equation. So keep that in mind. Here's the issue. That equivalence point calculation, if y'all remember, was like a really long calculation. HH is not going to get you out of it. Okay, so keep that in mind. You're still going to have to do that long calculation at the equivalence point. So let me show you real quick how to use HH in your titration calculation. This is actually the example that we worked in our weak acid, strong base titration curve. Okay, we had acetic acid with sodium hydroxide. And one of the points that we calculated on the titration curve was to determine the pH when 10 milliliters of sodium hydroxide had been added in the titration process. So I would have said, hey, I have a weak acid and a strong base. So that means I need to do NDSE, right? So here's my net ionic that I wrote between those. Here's my de-dilution work that I did. Here is my stoichiometry work. And then down here is all of my equilibrium work. Now, I'm going to show you how HH equation could save you some time. It happens right when I reach this end of the stoichiometry step. I see on this step that I have some weak acid here, as well as its conjugate base. If I have a weak acid plus its conjugate base, then that means I have a buffer solution. And if I have a buffer solution, then that means I'm allowed to use the HH equation. So, could I do it with equilibrium? Absolutely. Remember what I said at the beginning of this video. You can always do these problems with equilibrium. It always works. But here's an alternative option. Once I see I have a weak acid and a conjugate base, I can plug in HH. So I would have my pH equals my pKa. They gave me the Ka as 1.8 times 10 negative fifth, so I plug that in here with the negative log to get to pKa. Plus the log of my base, the conjugate base was 0.167 molarity, over the acid, which in this case was 0.666. And look at that. Hot diggity dog. It got exactly the same pH I got when I did equilibrium. So again, the whole point of the HH equation is so you can avoid equilibrium here if and only if you have a buffer solution. If you did not have a buffer solution, if you had no conjugate base present or no weak acid present because of the way the limiting reactant worked out, you could not have done this equation. Now, the other way, remember that you sometimes know if you're before the equivalence point, is that sometimes you're asked to do a stoichiometry to find the volume of the equivalence point. So if you know that you're doing a titration step before that volume, again, you could use HH because then you know, hey, I must be in the buffer zone. So take your pick on how you want to do these problems, but I'm going to warn you right now, be very careful if you're using this equation right here. Why? It only works for weak plus strong titrations, and you have to be before the equivalence point. If you're not, it won't work. But if you know for a fact that all those things are true, you can do HH instead of your E step on NDSE. All right, I hope you're feeling good about calculating with the Henderson-Hasselbalch equation. If you have any questions or need any help, please feel free to email me. Bye, guys.